to determine what the actual size of the proteins is in this gel, what we have to do is compare the migration of our sample, say this is our sample over here, with other proteins that we know whose molecular, their molecular weight. So that if we know that this is 50 and this is 100, this one should be somewhere about 75 or so. All right? The other important aspect of this is that some proteins are linked together, covalently together, by disulfide bonds, where two cysteine amino acids form a covalent bond between them, as shown up there. Running that tangle of two proteins in the gel is going to make things messy. So what we do is we break that bond by the addition of another compound called beta-mercaptoethanol. Beta-mercaptoethanol is added to the protein sample to break any disulfide bond that was already formed, or to prevent the formation of new disulfide bonds within the protein sample. Most people cannot easily pronounce beta-mercaptoethanol until you've been saying it for many years. So you can just say BME, and that'll be good enough. All right?
And it's a reducing agent. The breaking of the disulfide bonds is a reduction agent, so we call them reducing agents.
Okay? So let's put this into practice, going to INSAPOL. So here we have a gel that has been run through polyacrylamide gel electrophoresis. On the first lane, we have molecular weight standards. These are, again, are proteins that we know their size, which is indicated there, 35, 40, etc. So you notice, that some of them are 56, 67. Funny to put in a ruler, but that's the size of that protein, all right? So 56 might be, I don't know. I should find out what the identity of those proteins are. You can go back to the manufacturer and find that out. So, but we know their size. And then on the second lane, we have run a variety of proteins from some cell extract. So you can see that there's proteins of many different sizes. Some proteins are very large, run towards the top of the gel. Some proteins are very small. That's the smallest one that we can see. After running the gel, something that I omitted to say, the proteins themselves have no color, are invisible to the eye. So we have to have some way of detecting the proteins. And there's a variety of tricks to make them visible to us. For next class, we're going to be talking a lot about the use of radioactivity to detect proteins. And for that class, I need you to read some pre-class material on Canvas. So be sure to read that on the second module on Canvas by next class. So it's all about how do we detect proteins. So an easy way of detecting proteins, if you just want to see what's the overall presence of proteins in the gel, is by adding a dye that will bind to the proteins, color them, make them visible to you. All right? So in this case, the gel, after running, has been incubated with a dye to make the proteins visible to the naked eye. All right? So now we can see that there are some proteins that are very abundant. We know that because the band that illustrates that protein is really fat. There are proteins that are very low abundance. So all these guys over here, each of those individual bands are very skinny bands because there's very little amount of protein in there. So in the textbook indicates that this band corresponds to cyclin B because they've done other experiments to determine that. And this one is ribonucleotide reductase. So let me activate the question there. From the position on the gel, what would be your estimate of what would be the size of, okay, should be on by now. what is the size of cyclin B? And this is an easy question just to make sure everybody's able to enter their answer there. Okay, 73 responses, and half of you said that it's about 57 kilodaltons. Half of you say it's about 58 kilodaltons. That's a good, eyeball estimate. So somewhere between 57 and 58, I agree with all of you. All right, so that's how we do it, right? So of course you can do it more precisely by measuring the migration distance of each of the molecular weight standards, putting that into a graph, and then you can draw a line connecting the dots, and then you can measure the distance migrated by the different proteins that you want to know their size, and use the graph to interpolate in between them and be more accurate, all right? So, but eyeballing, good enough. However, there's a problem though. Turns out that if we look at the gene encoding cyclin B, and we look at the amino acid content, and we add the molecular weight of each of the individual amino acids, the predicted molecular weight from the gene should be 57. Not, sorry. Yes. 46, sorry, there it is, all right. Should be 46, all right. You all said it was much larger than that, all right. So something is not working, and there has to be a reason behind it, all right. So which of these reasons best explains that difference between the predicted molecular weight and the observed molecular weight on the gel? Okay, so now we don't have an agreement, all right? So I want you to talk to your neighbors and see what answer they had, and then if they try to find somebody who had a different answer than yours. If you have the same answer, you're not gonna be able to look at other points of view. So talk to somebody and then try to reach some agreement of what is the best answer for this question. Go.
And if you feel free to move around to find somebody with an answer different than yours.
I feel like it pushes me.
No, that sounds okay. Are you completely?
All right, let's take another vote. So go back to the question and answer, please. You can change your vote. Okay, I'm going to close it in 5, 4, 3, 2, 1. So we have consensus, semi-consensus. So the most of you did not say that A was correct because it contains a high fraction of hydrophobic amino acids. Hydrophobic amino acids are not going to be responding to the current, are not going to be modifying the speed at which is going to be a protein is going to be attracted to the positive electrode. So what could potentially change the behavior of the protein is by the number of amino acids, charged amino acids that it has. So the protein has to move to the positive electrode and is coated in negative charges by the detergent. So that's going to drag it to the positive electrode. That rate of movement, the speed at which it's going to be attracted, the strength of that attraction could be increased if it has a lot of negative amino acids. So it has more negative charges than average, and it's going to be attracted even more, so move faster. The opposite is true. If the protein has a lot of positive amino acid side chains, they're going to be resisting that attraction, and they're going to be slowing down the rate of movement of the protein. So what is true is that the protein has a very high proportion of positive amino acids, and that slows down the movement of the protein in the gel. So what you can see there is that while this is a really great technique to get an estimate of the molecular weight of a protein, it's not going to be 100% accurate because it will be modified by the content of charged amino acids in that protein. So we say that we get an estimated molecular weight of the protein, or apparent molecular weight.
But for most proteins, it's pretty accurate. It's unusual proteins that have either a high percentage of positive amino acids or are predominated by negative amino acids. So it's pretty good for most proteins.
Questions? Yes?
So the coating of SDS does not negate the charge, it just simply helps like diminish the effects of the charge?
Precisely. Yeah. All right. So SDS gels are going to be super important to really understand, and because of that, there's 2 homework problems that are due next week that make you think a little bit more carefully about protein gels. Seems very simple, but we can make everything a little bit more complex. So try to solve those problems. The homework problems, I should add, are to the level of problems that you will encounter in the exams. So they are a good way of measuring your rate of study and understanding of the material. If you have difficulty answering the problems of the homework, then you need to seek help. Right? There's no better way to learn than asking for help on how to solve that kind of problem. It involves a bit of logic and, of course, a good knowledge background of the topic at hand. We are going to be grading your homework exam by completion. So please do not look up the answers on the internet. It's going to be a waste of your time. It's not going to affect me, but it's going to affect you because you will not learn from the process.